take a look at this. It might not look like much, but what you're seeing is a special kind of crystal, one with the incredible power to turn wasted heat directly into electricity. This tiny material could fundamentally change how we think about energy, so let's dive in and take a closer look.
Okay, think about this for a second. Your car's hot exhaust pipe, or maybe the heat just pouring out of a factory smokestack. I mean, normally that energy is just gone, lost forever. But what if we could actually capture it? What if that waste heat could be harnessed to generate real, useful power? That's the challenge we're trying to tackle here.
And it's kind of crazy when you think about it. From our cars and computers to absolutely massive industrial plants, a huge portion of the energy we generate is just lost as heat. Finding a way to reclaim even a tiny fraction of that would be a total game changer for energy efficiency.
So how do we fix this? Well, the solution might lie in a really special class of materials called thermoelectrics. These are amazing substances that have this unique property. When you heat up one side and keep the other side cool, they generate a voltage. It's that simple. Heat in, electricity out. It is that direct. So why is this such a big deal? Well, for starters, these systems have zero moving parts. That means they're silent, they're super reliable, and they basically don't wear out. Plus, they produce zero emissions, which makes them an incredibly clean energy source. This tech could be perfect for just about everything, from capturing industrial waste heat to creating tiny, solid-state cooling devices.
Okay, so with that in mind, let's meet one of the most promising families of these thermoelectric materials, the Skutterudites. Their power lies in this really unique and fascinating structure that scientists like to call a crystal cage. You see, the job of a good thermoelectric material is a real balancing act. You need to let electricity flow through it easily, while at the same time, you have to block the flow of heat. Think of it like this. You want to give the electrons a superhighway to zip through, but you want the heat vibrations, what scientists call phonons, to get stuck in a massive traffic jam. And that is exactly where this crystal cage idea comes into play. The Skutterudite forms a rigid, stable lattice. That's the cage. But inside this cage, there's a loosely held guest atom. This little guy can rattle around, and that rattling action is unbelievably effective at scattering and blocking heat. And here it is. You can actually see that cage in action, formed by germanium and platinum atoms. And right there in the middle is our guest, the praseodymium atom. It's this one-of-a-kind rattler-in-a-cage structure that gives these materials their incredible heat-blocking, electricity-conducting power. Now let's zoom in on the specific material from the research we're exploring today. Its name? Well, it's a mouthful. Praseodymium platinum germanide, or for short, PrPt₄Ge₁₂. This is the star of our show. I love this slide from the research paper. It's basically a complete cheat sheet for this material. Now don't worry. We're not going to get lost in all the details here, but you can see how scientists map out all its properties. They look at its basic structure, its stability, how it behaves with heat, and then they get into its more exotic talents, like its magnetism, its optical properties, and of course, its thermoelectric performance. We're going to touch on a few of the really key features.
Okay, so first things first. Before we get all excited about any of the cool exotic properties, we have to ask a simple question. Is this stuff actually practical? And the research confirms that yes, PrPt₄Ge₁₂ has a highly stable structure. It's fundamentally sound, and that is the very first box you have to tick for any real-world application. All right, so we've established that it's stable. Check. Now let's get to the really fun part and explore the unique combination of powers that makes this material so special.
So how do you even measure how good one of these materials is? Well, scientists have a score for that called the figure of merit, or ZT. And honestly, the easiest way to think about it is like a GPA. A higher ZT score just means the material is an A+ student at converting heat into electricity.
So, what's the grade for our material? Drumroll, please. The research finds a peak ZT value of about 0.26. Now, I know what you might be thinking. That number by itself doesn't sound earth-shattering, but hold on. The real story is at what temperature it achieves this score.
And this is the key. Take a look at the graph. The material hits its peak performance at a blistering 700 degrees Celsius. That's 1,000 Kelvin. This makes it a fantastic candidate for the hottest of hot environments, like capturing waste heat directly from engines or industrial furnaces, places where many other materials would just completely fail. But wait, there's more. Turning heat into power isn't its only trick. This material, well, it also has a magnetic secret.
Okay, this chart is absolutely fascinating. It shows the magnetism doesn't come from the main cage structure. It's coming almost entirely from that one little guest atom, the praseodymium. This creates a weak magnetic effect called paramagnetism. So why does that matter? Because having both thermoelectric and magnetic properties in one material, that opens the door for wild new technologies, like Spintronics, which could lead to super fast and efficient computers.
So it's stable, it's got these cool electrical properties, but can you actually build anything with it? I mean, is it tough like a wrench, or is it fragile like a teacup? In material science, we call this the difference between being ductile, meaning it can bend, and being brittle, meaning it just snaps.
So what's the verdict? Is it tough enough for the real world? Yep, the research gives us a clear answer. Scientists use a measure called PrPt₄Ge₁₂, ratio, and basically, any score over 1.75 means a material is tough, not brittle. The bottom line? This material scored a 2.23. That means it's absolutely ductile. It's durable enough to be made into reliable, real-world devices. It bends, it doesn't break.
All right, let's pull all of these threads together. What does all of this, a stable, tough, high-temperature thermoelectric that also has magnetic properties, what does it all actually mean for our future? Well, it means this material is definitely not a one-trick pony. It's more like a Swiss Army knife. Yeah, its main job could be turning waste heat into power, but its other unique properties, the magnetic, optical, and maybe even superconducting potential, make it a candidate for a whole suite of future technologies, from advanced sensors all the way to components in quantum computers.
And that brings us all the way back to where we started. Every single day, we waste enormous amounts of energy as heat. But this kind of detailed research into versatile, high-performance materials like this one gives us a powerful new toolkit. It suggests a future where the heat from our engines and our factories is no longer just waste, but a valuable resource just waiting to be tapped.